We were just looking at the peptide bond and the adjacent angles to that peptide bond, the bonds that we actually have some rotation on. Those are our phi and psi angles. Now, those phi and psi angles are important because it gives you an insight into how much rotation that your protein can have and how much you can expect an amino acid to rotate in 3D space compared to the placement of that peptide bond and where that amino acid R group can go. Now, with that said, there are some limitations. So some phi and psi combinations are unfavorable because of steric crowding or steric hindrance of one another. And so what that's going to do is going to say there's some limitation. Okay, now some phi and psi angle combinations are more favorable because they have the chance to form favorable hydrogen bond interactions along with that backbone. So there is a visual for that known as a Ramachandran plot. That shows the distribution of phi and psi dihedral angles that are found in a protein. Now, this shows the common secondary structural elements that ultimately are produced and reveals regions of unusual backbone structure. So if we look at this display right here, this is a Ramachandran plot. Now on our y-axis, we have rotation of our phi angle, or our phi angle rotating from negative 180 to positive 180 degrees. On the x-axis, we have our phi angle, which rotates from negative 180 to positive 180. Now what's important about this is that this is a display for proteins in general. So there are some proteins that are not going to kind of cover all of these angles, but this white region is the region of unfavorable reactions or unfavorable bond pairings, and the blue region is those favorable bonds. So there are some points on this graph that are highlighted. For instance, beta sheets, you have anti-parallel and parallel beta sheets, you have right-handed twisted beta sheets, and then you also have left-handed alpha helices and right-handed alpha helices. So what these show are the bond angle pairs that are going to exist within these different things. Now, the third one that I didn't really mention, beta sheets and alpha helices, is this collagen triple helix. So collagen is a structural protein, which we'll talk about a little bit, and it forms a unique structure known as a triple helix. Like I said, we'll get into the structure of collagen a little bit later. But one of the things that's worth noting is that a large number of these bond angle pairs are really not favorable. So if you thought about a phi angle being positive 180 degrees, well, or let's say positive 150 degrees. So a phi angle positive 150 would be approximately there. There are basically no psi angles that are going to match up with that would make this a favorable bond angle pairing. So the Ramachandran plot kind of shows you that of all the different rotations in three-dimensional space that a protein can have, and that R group can move around based on those phi and psi angles, there are some limitations to it simply based on steric hindrance. So here's another display of that Ramachandran plot. Rather than it being a density map, instead we have analyzing a specific protein where those angles or what angles are actually present in a specific protein. Now, secondary structure. This is the structure that is going to be stabilized by backbone hydrogen bond interactions. Secondary structure refers to the local spatial arrangement of the polypeptide backbone. The key here is the word local. So we're thinking about kind of zoomed in. It's almost like if a protein is a city, a secondary structural element would be like a neighborhood or something like that. Now, there are two common arrangements of secondary structures. There's the alpha helix and the beta sheet. The alpha helix is stabilized by hydrogen bonds between nearby residues, and the beta sheet is stabilized by hydrogen bonds between adjacent segments that may or may not be nearby. So what that means is that when you think about an alpha helix, it's going to be amino acid number 10 and 13 or something, and 18 that are all involved in the formation of an alpha helix, whereas a beta sheet might be made up of amino acids 10 and 275. What these two amino acids, 10 and 275, how they're able to be involved is because the overall peptide or polypeptide backbone is going to position them so that they're nearby. So they're adjacent, but they're not necessarily nearby. Okay, irregular arrangement of the polypeptide chain is called a random coil. So generally when you think about a secondary structure, you should be thinking about an alpha helix, a beta sheet, and anything that's not an alpha helix or a beta sheet is going to be a random coil. So don't think that it has to be, or the secondary structure has to be an alpha helix or it has to be a beta sheet. It's entirely possible that there are residues within a secondary structure that are simply random coils.